One of the major early commercial successes in the history of artificial intelligence was the rise of expert systems. And in this lecture, I'm going to talk about the history of them. However, this term is almost never used anymore, and understanding why is helpful for understanding some of the other changes that have occurred in the past few decades of artificial intelligence. So what is an expert system? An expert system is a symbolic system aiming to simulate the diagnostic or decision-making abilities of a human expert. The very simplest expert systems are based on the idea of a field guide or flow chart, which predates computers. So, for instance, the What Tree Is That guide from the Arbor Day Foundation, it starts by asking you, are you in the Western United States or the Eastern United States? And then it asks you about the tree you're looking at. Does it have needles or leaves? And if it has leaves, what pattern are those leaves in? And so on. And it goes through these questions until it identifies the tree. I think it's useful to think of this as a kind of artificial intelligence, even though it doesn't involve a computer. And in particular, it's like an expert system. The experts at the Arbor Day Foundation have used their knowledge of the trees of North America and the simplest features that can be used to identify them to create an algorithm that an ordinary person can follow and get the same diagnosis that an expert would give. Of course, more interesting expert systems take advantage of the processing power of computers rather than the ability of an ordinary person to identify what leaves look like from a picture. One of the earliest important expert systems was Dendrel. This was a program developed at Stanford University to help chemists identify chemicals from the sizes of fragments that were found in a mass spectroscope. That is, they knew how many atoms of each element were in the chemical, and they knew the spectrum of the different sizes of some of the pieces that broke off in the mass spec machine. And they wanted to figure out which atoms must be connected to each other in the original molecule. The first thought is that they would just have the computer work by brute force and generate every possible structure for the molecule and calculate what is the spectrum of piece sizes that it would produce, and then see which one of those is closest to what is observed. However, once there's a few dozen atoms in the chemical, there's tens or hundreds of thousands of possible structures. So this becomes too complex even for the computational systems of the time. And this is late 1960s, early 1970s. However, they realized that the human experts who worked with these mass spec machines had discovered some important patterns. So for instance, don't worry about any of the details here. If there's a carbon double bonded to an oxygen that forms a bridge in the molecule, then the spectrum will include a piece of size 28, that carbon and oxygen, and also two different pieces, the left half and the right half, that would each appear with sizes plus or minus 28. So if you can see that pattern in the spectrum of sizes, then that tells you a major part of the structure, and you can simplify the problem. You don't have to consider every structure. Now you just have to consider the ones with the C and O double bonded to each other. And so to design Dendrel, they talked to many different organic chemists and found dozens of these rules of thumb that the humans were using, which allowed the computer to very often cut the number of possibilities required down to a size that then the computer could use its distinctive brute force to solve. Now, in the early mid-1970s, during the first AI winter, when corporate and government funding for AI had dried up after the hype of the 1960s and the failure of early neural networks, some of the other researchers at Stanford were inspired by Dendrel, and in fact, some of the people who worked on Dendrel went on to work on this new system that they were developing for the medical school called Mycin. And this one was intended to help doctors identify different blood infections to figure out which antibiotic might be most helpful. In this case, there's no brute force combinatorial method available like there was with the molecules. And also, this was a very difficult problem. Doctors very often disagreed with each other about what was best. However, they were able to use this same idea. They talked to all of the human experts who worked in this field and figured out what are the heuristics that each of them is using. And they figured out a way to write all of these into a language that could be entered into the computer system. And then what they would do is have the computer figure out which different rules might be the best ones to apply in any given context. And importantly, unlike the rules from the Arbor Day Foundation for identifying a tree, or the rules from Dendrel for the organic molecules. The rules for identifying blood infections were all more or less uncertain because of all the variation of individual bodies, all the possible interactions between infections and diet and medicine and other things like that. And so some experts who knew one set of factors that were relevant for patients who had maybe blood infections during cancer treatment, and other experts knew other factors that were relevant for patients who had blood infections related to diabetes. Often they weren't both in the room at the same time when a patient had an infection. So it was very helpful to have a single computer system that could weigh the importance of all of the multiple rules that no individual human had an intuitive understanding of. And furthermore, at the end of the process, when the computer made its recommendation, it could say specifically which rules in its rule bank that it used. And this could help the doctors involved understand why the recommendations were being made. And although Meissen did make recommendations that on average got a rating of 65% from human judges, which is better than the ratings that actual human doctors were getting, which were more like 50 to 60%, because these are very hard problems. It still wasn't used much in practice because this is still the early 1970s. There weren't personal computers or desktop computers. Computers took up a whole room, and they didn't have them in the hospital where it was needed. But Meissen did set the general pattern that they could then use to develop other expert systems. They would first develop some sort of knowledge base, including all the different rules and heuristics and patterns and defaults that they gathered by interviewing human experts who worked on the problem in question. And they had to figure out, how do you represent all of this knowledge in a way that might be usable in a systematic language that a computer could process? And so this involved what they call a knowledge base, which is much more structured than something like a database or a spreadsheet. In those things, you just have a bunch of numbers and cells, whereas here you have to understand, what sorts of entities does the computer need to be thinking about? Is it people and diseases? Is it who knows what? And so once you've designed what's the structure of the knowledge and gathered the rules from the experts, they could then use an inference engine. And much of the research in artificial intelligence in the 1970s was devoted to identifying what are good inference engines for dealing with a bunch of rules that might be in conflict with each other or that might be more or less certain or uncertain. And over the next several years, there were a bunch of these expert systems designed, and they started working well enough that by 1981, the Digital Equipment Corporation, DEC, had found out about it and decided to implement their own expert system to help their computer designers configure orders for clients. And then within the next year, that worked so well that DEC developed another expert system to help their chip designers figure out what's the best way to organize the circuits on their new chips. And within the next couple of years, they were doing a lot of their processes this way, and it was working better than trying to get all of the many experts into the same place at the same time and devote their thinking power to each individual problem. They could get them all involved once to design the knowledge base and then apply this across their organization. And in the early 1980s, the Japanese government also got interested and they funded a project to design a whole new generation of computers that would make expert systems easier to implement. This being the early 1980s, American and British companies were at the time worried about Japanese companies taking over the entire economy, so they all started rushing in too. And another important and relevant development is that in the early 1980s, this is the time at which desktop computers started becoming common. So it was more possible for working professionals to have a computer in the room with them while they were doing the job. And so this rise of expert systems was one of the important things that ended the first AI winter. It got corporations interested in artificial intelligence, and it provided not just investment, but actually a whole lot of working AI systems that were making money for companies. But by the end of the 1980s, this boom started running out of steam. While there was some improvement in the inference engines that people were working with, it became clear that the biggest thing that you needed to do to design an expert system and to make it work well depended on improving the knowledge base. However, the knowledge base required sophisticated input from human experts. First, you had to get all the experts together to figure out what's the right way to even represent knowledge in this domain. And then once you've done that, you have to sit down and talk with each of the experts to understand what are the rules that you're using, what circumstances do you use them in, how do you know how certain to be when you're using that rule. And this took a lot of hours of the experts' time. And these experts who were needed to be consulted to design the system were often the highest demand employees at the company. They wanted them actually out there making decisions, not just telling someone how to maybe someday improve the computer system that helps other people make decisions. And so getting these experts to sit down with the AI engineers was often very difficult. Uh, and although expert systems could often perform better than any individual expert, by putting together the knowledge that different experts in different subparts of the problem had gathered, they very clearly couldn't come up with anything truly new. All they did was take the best of what humans already knew. And so by the late 1980s, the rise of expert systems had mostly run its course. There were still plenty of them being developed, but there was not much new research involved in it. And this led to a second AI winter when corporations and governments started cutting funding for AI. Another thing that's relevant is that at this time, in the late 1980s, the backpropagation algorithm for training neural nets had just started being applied. And while neural nets had been abandoned in the late 1960s because of some apparent limitations, by the late 1980s, it started becoming clear that these were valuable. And one of the big things that neural nets could do is that they had the ability to extract information from just basic labeled training data that was gathered incidentally in the course of operations. They didn't require expert judgment to build into the knowledge base. Furthermore, because the neural nets are just extracting patterns from the data, they could sometimes even identify patterns that no human had identified. Now, neural nets did have some disadvantages, and those are still disadvantages that we're dealing with today. One of the things is they learn patterns that no human would generalize, which means often it's very hard to explain why they came to the decision that they made. And furthermore, they sometimes make apparently crazy decisions that make no sense to humans because they're picking up on some pattern that may or may not be real, or maybe they're missing some background knowledge. So just as expert systems were developed by academics during the first AI winter and then led to a commercial boom about a decade later, neural nets were a major product of academic research during the second AI winter in the 1990s, and they eventually started showing commercial success a few decades later in the mid to late 2000s or even the 2010s.